You know, for the longest time, we've basically treated orthopedic implants as simple spare parts, just inert pieces of metal meant to replace something that's broken. But that's all changing. Right now, we're in the middle of a massive revolution, one that's transforming these implants from just passive replacements into sophisticated, active tools that actually work with the body to heal and regenerate itself.
Okay, so let's dive right in. To really get our heads around this new generation of implants, we're going to look at the four big challenges that the traditional ones have always faced. First, the physical mismatch with our own bodies. Second, their total inability to speak the language of our cells. Third, that constant, brutal war against infection. And finally, the really tricky one, befriending our own immune system.
Right. So let's tackle the first big one, which is probably the most obvious, the problem of form and force. How in the world do you create an implant that doesn't just fit, but actually functions like it was always meant to be there, as a seamless part of you?
So, on one hand, you've got these incredibly complex shapes and defects, maybe from a bad accident or a tumor, that your standard off-the-shelf implant just has no hope of fitting properly. But there's this other, much sneakier problem. Solid metal implants are way stiffer than our bones, so they end up carrying too much of the weight, shielding the bone around them from the normal stresses it needs to stay healthy and strong. This whole phenomenon is called stress shielding, and it can actually make the bone waste away, which leads to the implant loosening and, well, failing.
So what's the game changer here? It's additive manufacturing, 3D printing. It's this incredibly precise four-step process. First, you get these super high-res scans of the patient. Then you create a perfect digital blueprint of the implant. After that, a 3D printer builds the custom implant, layer by tiny layer, from metal powder. And finally, you can even print patient-specific guides to make sure the surgery is absolutely perfect.
And here's the truly brilliant part. This is how 3D printing solves that invisible stress shielding problem. Look at solid titanium. It is incredibly stiff, way up there around 110 gigapascals. But by printing it with a porous, bone-like internal structure, we can dial that stiffness all the way down into a range that perfectly matches our own bone. Just like that, problem solved.
Okay, so we've got the physical fit down, but now let's zoom in, way in, to the micro scale. Because even with a perfect mechanical fit, that implant is still a complete foreigner. It's a silent object that doesn't speak the biological language our cells use to talk to each other.
You see, a standard titanium surface is what scientists call bio-inert. Basically, it's a silent bystander. It doesn't harm you, sure, but it doesn't help either. It gives off zero active signals to encourage bone cells to grow. And this passivity means the healing process is painfully slow. We're talking up to 6 months, and you end up with a weak connection, not a true living bond.
So the real breakthrough is realizing we have to stop thinking of these things as just passive scaffolds. We have to engineer them to be active players in the healing game by tweaking the surface at the nanoscale, creating tiny textures, applying coatings that mimic actual bone, and even doping the surface with essential metal ions. We can get the implant to actually talk to the body's cells.
And listen, this isn't just some lab theory. The results are absolutely stunning. Just by weaving a bit of an essential element like zinc right into the titanium surface, you can boost the adhesion of those bone-forming cells by a full 40%. They literally grab on tighter and faster.
And if you thought that was cool, check this out. It gets even better. Swap out the zinc for a different ion, magnesium, and you can literally supercharge the growth of those same cells by an incredible 4.5 times. We're not just hoping the body heals, we're giving it clear, powerful instructions to get the job done, and fast.
All right, now for a problem that is the stuff of nightmares for any surgeon: infection. An implant provides this perfect, clean surface for bacteria to move in and set up shop, creating a nearly impenetrable antibiotic-resistant fortress right inside your body. This fortress, it's called a biofilm. The bacteria attach to the surface and start secreting this protective slime that shields the whole colony. It's a huge cause of implant failure, and because regular antibiotics just can't get through that shield, fixing it often means more painful and complicated surgeries.
So how do you storm this fortress? Well, the modern approach is brilliant. You stop trying to send in armies of antibiotics from the outside, and instead you build the weapon right into the walls of the city. By doping the surface with an element like copper, we can create an inherently antibacterial surface that achieves over 99% effectiveness against common bacteria. It just kills them on contact.
Okay, on to our last big hurdle. And this one's a tough one, because we have to deal with the body's own internal police force, the immune system.
It's hardwired to recognize and attack anything it considers not self.
This is what's known as the foreign body response. The immune system's playbook is pretty simple: attack and destroy any invader. But when it can't destroy something big and solid like an implant, it does the next best thing. It walls it off. It wraps the implant in this thick, fibrous scar tissue that completely isolates it from the rest of the body, killing any chance of it ever truly integrating.
You see, for the longest time, the goal was what they called immune silence, basically trying to make the implant invisible like a stealth bomber so the immune system wouldn't notice it. But the new way of thinking? It's so much smarter. Instead of hiding, the goal is to have an immune dialogue. The idea is to actively steer the immune response, convincing it to switch from attack mode to repair mode.
And this just lays it out perfectly. You've got two roads the body can take. The old way, with the traditional implant, triggers this aggressive response that leads to constant inflammation and that fibrous wall. A total failure. But the new engineered surface? It's like a diplomat. It calms the situation down and actually guides the immune cells toward a repair mindset, promoting healing and success. It literally turns a potential enemy into your greatest ally.
Okay, so we've tackled the shape, we've tackled the stiffness, we've taught it how to talk to cells, how to fight off bacteria, and even how to make friends with the immune system. So what happens when you put all of these incredible breakthroughs together? What does the implant of the very near future actually look like?
It looks like this. And it's not just a chunk of metal anymore, is it? It's a multi-scale, multifunctional engineered system. It has that patient-specific 3D printed form, a porous core to perfectly mimic bone's mechanics, and this incredibly sophisticated multi-layered surface that's bioactive to speed up healing, antibacterial to stop infection, and even immunomodulatory to guide the body toward regeneration.
But you know how it is? Science never, ever stands still. The evolution is already pushing beyond even this incredible static design. The next great frontier is creating smart implants with dynamic interfaces that can actually change and respond to their environment over time.
I mean, some of the stuff they're working on now sounds like it's straight out of a movie. We're talking about surfaces that can release medicine the very moment they sense an infection starting, or 4D printing, where an implant can literally change its shape over time to adapt as the body heals. They're even working on integrating living cells to create true, living, tissue-engineered parts.
So what this all points to, it's a huge, profound shift in how we even think about this stuff. We're moving away from inert pieces of hardware and toward active biological partners. And that leaves us with this one final, really powerful question to think about. What if the ultimate goal of an implant is no longer just replacement, but regeneration?